I'm David Tronis. I've been doing reliability engineering analysis and improvement for 25 years in different industries. This is just one in a series of quick summaries on different topics relating to managing equipment reliability as well as safety and performance. Welcome to Weibull Analysis in 5 minutes or less. I would certainly like to see more companies stop using MTBF for a metric, and I'll let you know why, as well as potential frequency ratings from FMEAs. So I want to show you a much more serious and powerful approach to measuring and improving reliability. Let's say we have 4 machines that have about the same average time between failures, or MTBF. We might infer that they are all operating alike. However, averages are misleading. A better approach would be to look at the actual times to each failure. Here you can start to understand a lot more. Out of the 4 pieces of equipment, case number 1 certainly looks different. And even better than just looking at raw numbers is to put the data into separate frequency charts. Now you easily understand more. At the very least, you can see all the machines are operating very differently. One of the prerequisites to do even better is to move beyond failures. Failures really just pertain to how a machine fails to perform its function. Like with a new car, the door won't close. Just using that level of information does nothing to enable a team to drive improvements with data. We need to go further to failure modes, that is, the way it failed to perform its function, like latch won't close, and then look at the wear factors, which refer to the mechanism which leads to the eventual failure mode. Perhaps the number of high force closings. Let's take a look at the next level, which is a Weibull plot. By the way, Weibull refers to the Weibull distribution. The x-axis is on a log scale, the amount of time, wear, etc. before the failures occur, and the y-axis shows the cumulative probability of failure. Now, when the points are all plotted on this special paper and they fall in a line, it basically means the data fits this distribution. The beta, or the slope of that line, gives insight as to the underlying nature of the failure mode. Now, when the slope of the line is less than 1, it infers that, or in other words, it's flatter, it infers that an infant mortality mode is being seen, often caused by things such as inconsistent assembly, quality, inconsistent installation, etc. Seeing this says that instead of just focusing on improving the average, the important thing to do is to find the source of infant mortality and then eliminate it. The same thing applies when you're talking about determining a PM frequency. Now, when the slope of the line is much greater or steeper, for instance 5, that's the rise over run, it indicates a rapid wear-out failure mode, which might be typical for bearings or when you have corrosion, or maybe it's just end-of-life modes. Also, this case provides clear direction on the recommended frequency of a PM or replacements. Other uses for Weibull analysis: how many machines could I test for how long without failures to be 90% confident that we did eliminate the failure mode? Based on those charts for different failure modes, what is the optimum number of spares we should keep? Based on the analysis, could I afford a 10-year warranty? How many of these machines will fail before we get the improved parts out to the customer? And what is the probability of this type of safety incident occurring in the next year? Contact me anytime for more information, or if you need help, and I'd be glad to tell you about the various services I provide.